So today, what we're going to discuss is we're going to discuss independent and dependent events. All right? So we're going to discuss independent and dependent events. So an independent event occurs when the occurrence or non-occurrence of one event doesn't affect the probability of the other event. So if I was rolling these two die, if I were to roll that die and it's sitting on the table, all right, whatever's on that die, is that going to affect what's going to happen with this one? No. So these are independent. The two rolls don't affect each other, all right? And so that's an independent event. Now we have an equation for an independent event. It's going to be on your formula sheet. It will say independent event, all right? And so if I have two events and they're independent, then the probability A times the probability B would equal the probability of both. All right? So I'll take A times B, and then that would give me both. Okay? So here's the first little example that we're going to work. We have a container, we have a bag, and it's got 3 red and 2 white marbles or balls in that bag. So I got 3 red, 2 white. I have a separate container that has 1 red and 4 whites in it. All right. If I picked one out of the first container, I picked one out of the second container, would this be independent or dependent? Independent, because whatever I pull out of this one's not going to affect what's over here. All right. So they're separate. So it's independent. Now, the first thing it asks me is this, okay? So if I reach into this one and grab a red, and I reach into this one and grab a red, what would be the probability that I get red, red? Okay? So what's the probability to get red, red? Well, what's the probability to get red out of that container? 60%, or 3 out of 5. There's 5 in there, 3 of them are red. So 3 out of 5, or you could say 60%. Times, what's the probability of getting red out of the other one? 1 out of 5. So the probability of drawing red, red would be 3 out of 25. Okay? So since they're independent events, we find the probability of each one, we multiply them together, and that gives me the probability that they both happen. Okay? Going to question B. What's the probability that the balls are different colors? What would that look like? What would my result look like if I drew? Say again?
Red and white.
Red and white. I could draw red out of this one, I could draw white out of this one. Is that the only way? I could draw white and red, correct? So there's actually 2 events here that would work. So I'm going to draw red, white first. So if I drew a red and white, red out of the first one would be 3 out of 5. White out of the second one would be 4 out of 5. If I were to multiply those together, I get 12 out of 25. That's the probability that I draw a red first and then a white. I'm going to do the other one as well now. I'm going to do white and red. So white out of the first bag would be 2 out of 5. And a red out of the second one would be 1 out of 5. So to draw a white red, that would be 2 out of 25. Now, if there's more than one way to get the result, we find the probability of each way, and then we would add up all those ways together. So 12 out of 25 plus 2 out of 25 would give me 14 out of 25. Okay? I didn't do that on the first one because how many ways is there to get a red, red? There's only one way to do that, right? Red, red. Okay? Now, last question here. It asked me, what's the probability that I get at least one of them red? So what would my result, one of them white. Sorry, I can't read today. What's the probability that I get at least one of them white? What would make my results look like if at least one of them's white?
Red, white.
Red, white.
White, red.
White, red.
Or white, white.
Or white, white would work as well. So the 2 that we've already done plus an additional one. So I could do white, white. I could do white, red. Or I could do red, white. If I got any of these results, then I would have at least one of them being white. All right? Well, I already know white, red. White, red is 2/25. Already know red, white it's 25/25. The last one that I need to go find would be white.
Pretty sure it's 12.
Did I say something else?
It's 25/25.
Man, having a hard time today, sorry, 12/25. I'm writing it correctly and saying it wrong, huh? So do what I do, not what I say, right? Alright, at least for the day. Alright, so how about white? How do I find white?
2 out of 5 times 4 out of 5.
2 out of 4, 5, and 4 out of 5, that's correct. Yeah, so that would be 8 out of 25. So I can add all those up. So that would be 10, that would be 12 more, which would be 22 out of 25. So I have 22 out of 25% or chance that I'm gonna get at least a white. Alright? Before I move on, is there another way that we could possibly work this?
I mean, you could start off with both being red and just take 1 and subtract that.
Okay, take 1 and subtract this. How many different outcomes are there in this problem?
4.
There's 4 different outcomes. How many outcomes do I have from the first container? 2 outcomes. How many outcomes do I have from the second container? 2. So 2 times 2 would give me 4 different outlooks. I have white, I have white, red, I have red, white, and I have red. Those are the 4 different things I could have, right? Well, if I look at this one, it's saying I want all these except I don't want that one. So everything is one whole. So I could go one whole minus the part that I don't want, which I did that in the very first step. I did red in the first step. So 1 minus that. So how would we represent the 1?
25 out of 25.
See, that's what I was thinking a while ago. Here's my 25 out of 25. 25 out of 25 minus the 3 out of 25 gives me the same 22 out of 25. All right. This one you could have done it either way. All right. But if you have like 8 different outcomes, I don't want to do 7 of them and add all those up. I would rather do the one that I don't want and subtract it. Okay? Make sense? All right. So let's go look at the problem that I asked you to do kind of as a warm up. All right. Anybody get an answer for if I were to spin this spinner twice, what's the probability that I get 2 greens?
25%.
25%. All right. What's the probability that I get a green on the first spin? 50% or 1/2. What's the probability you get a green on the second spin? Same thing, right? Are these independent events? Because I spun something on the first one, is that going to affect my next spin? No. So 1/2 times 1/2 is 1/4, or you could have said 25%. Okay? What's the probability that I get no reds?
It's 3/4 times 3/4.
It would be 3/4 times 3/4. Because what's 3/4? 3/4 is the probability of getting a green or a blue, which is not a red. All right? So 3/4 times 3/4 would be 9/16. Now, that's the easiest way to do that. Could you have gone through there and said, okay, I don't want a red. So my options would be blue, green, blue, and green. I could find all 4 of those and add them together. Would that work as well?
It'd take longer.
It would take longer, but it would also work, okay? But yeah, so this was definitely the shorter way to work that one, but I could have worked it that other way also, okay? All right, the last one here. What is the probability that I get 2 different colors? When I spin, I get 2 different colors. Well, how many different outcomes do I have there?
3, but you can't get 2 colors on one.
Yeah, well, 2 colors on 2. So I don't want to go what? Red. I don't want to do that. I don't want to go green. I don't want to go blue. All right. So I want to go like red, green, or red, blue, green, or blue, red, or green, red, or green, blue. All right. So there's 6 different things that I want. I don't want to find all of those 6. Okay. So what I would probably do is I would probably find the ones that I don't want to do here. So what is the probability of red? a 16th. 1/4 times 1/4, all right? So the probability of red is 1/16. What's the probability of blue? Also 1/16. It's the same area, correct? And we already found the probability of green, which is 1/4. So, or 4/16, yeah. So we would take one whole, which is everything, and we would take off the 3 types that we don't want. We don't want those 3. Okay? How would you write the 1? 16 over 16, and 1 over 16, and 1 over 16, and somebody may mention a while ago that we would change this to 4 over 16. So 16 minus 1 minus 1 minus 4 would be 10/16. You could reduce it if you like. Okay? Everybody okay with that? There's quite a few little good ones in there as we were working. Again, you could have found all those other different options if you wanted to, but trying to show you that everything adds up to be 1. That's a big important part. For sure in the next unit as well. Okay? Everybody good there? All right. So that's independent. All right. The next thing we want to talk about is we want to talk about dependent events. All right. Dependent events and conditional probability kind of go together. Whenever I'm doing conditional probability, there's normally dependent events involved. All right. So, like I told you yesterday, I have a child that she will roll this right here, and if we're playing Monopoly or whatever, got a 2 there, and they're going, oh, okay, I can't get a 5 here, because that would give me 7, and then I'm going to land on jail or whatever, okay? And so, if that's already says something, then this is kind of dependent on what's already there. Make sense? All right, so we could have some dependent things there. So, dependent events, the occurrence or not occurrence, affects the probability of another event. Here is the 4th formula that's on your formula sheet, okay? I'm glad that they finally wrote it this way. They used to write it like this on the formula page right there, which all that is they multiplied by the probability of B on this side and cleared the fraction. But normally we don't use it in this manner. Normally this manner is what the way that we use it in a lot of problems. Now, what's the symbol in there that looks kind of weird? The I, it's a vertical bar right there, is what that is. Now this means given. So if I were to read this right here, it's the probability of A given B. All right? The probability that A occurs given that B occurs. Okay. So if I were to do this, if I were to ask you, okay, if I were to go down to the cafeteria at lunchtime or whatever, and I were to say, okay, if I just picked a random person and started talking to a random person down there, what's the probability that they're a junior? How would we do that? Well, we know how many juniors are in the school. We could go look it up, right? 500 and something juniors or whatever. And we could go figure out how many total students there are in the school, all right? And the probability that I picked a junior would be 500 or whatever out of the total population. Okay? It'd be kind of like a experimental deal. What'd you say?
So what if somebody's absent?
Okay. Well,
Or that-
that might change it a little bit. Okay. But in theory, that's kind of what happened. Well, what if I did this? All right. What if I said, what's the probability that I pick a junior given that they're in an IB class? What did I just do? I shrunk the sample space, right? I'm not looking at near as many people now, am I? I'm only going to go look at a list of all the IB people, all right? And then on that list of IB people, then I'm going to find how many juniors are on that list, all right? And so when we do conditional probability, one of the main things that happens is it shrinks my sample space. So normally when we have a conditional probability, it normally lessens the amount of people or the amount of things that we're looking at, all right? So it kind of narrows our focus. So our conditional probability does that. Okay. So we're going to do a couple little conditional probability problems, and then we'll be finished for the day. Okay. All right. So I want you to, on this page right here, it's got a couple little formulas, but we can work through those later. Not worried about that. But I want you to read this little scenario right here, and then we'll discuss it. So on this one right here, what do you think you might use to help you solve this one? Probably a Venn diagram. Looks like it would be pretty good there. All right. So if I were to draw my Venn diagram, I have the 53 staff members that I surveyed. I've got my tea drinkers and I have my coffee drinkers. All right. And what would you place first in this situation? The 10 that don't do either. That's correct. Where do those go? Outside the circles, but inside the box. Okay, so there's the 10 that don't like coffee or tea. I'm not sure what's wrong with that. Okay, all right. Now, the next question asks is how many drink both tea and coffee? So the people that I surveyed, how many drink both tea and coffee? We did a little formula for that on Tuesday. So I'm going to use that formula. So that formula that we used on Tuesday was the probability of A or B is equal to the probability A plus the probability of B minus the probability of A and B. Okay? So that was that combined events formula. This is probably the most important formula in this unit. The other ones are important, but this was the one that you're probably going to use the most. Okay?
These are on our formula.
They are on the formula page. Okay? There's 4 variables in this one. What do we know? What can we plug in? What can we say probability A is? 36 that they're a tea drinker. So we'll say A is a tea drinker in this case. So 36 plus the probability that I drink coffee. 18. All right. Do we know how many of them drink both? No, but that's actually what it's asking, correct? So that's really my variable. All right. So minus X equals, this would be how many of them drink coffee or tea or both. How many of them drink coffee, tea, or both?
Would you add them?
Say again?
36 plus 18.
36 but 8, not quite.
43.
43. How'd you get 43?
Subtract it by the people
Mhm. So these 10 don't do either. I know there's 53 people that I surveyed. 10 don't do either. But 43 do some version. Tea, coffee, or both. All right? So this is 43 that goes right there. Good. All right? Now, 36 and 18, I believe is 54. Is that correct? No? I think I'm okay on that one. All right? All right. Your name's not even Josh. So I have negative 11 equals negative X.
Hey, you just got clocked on recording.
All right?
This is going on YouTube.
This is going on the YouTube. Hello, YouTube.
All right. Now, that right there, 2 negatives make a positive, so 11 goes there.
I'm gonna watch the video.
All right. So how many staff drinkers drink both tea and coffee? Is an 11 an acceptable answer there?
It's 11 out of 53.
Does it have to be 11 out of 53?
No.
Not on this one.
Many people.
Okay. If it asks what? Probability, then it would. But 11's perfectly fine on that one. Okay? But now it switches gears a little bit here in the middle of the problem. One staff member is chosen at random. Find the probability that he drinks tea but not coffee. Okay? So now it's probability. Now I have to have a number between 0 and 1. Okay? Which means I need to do a fraction. So how many people drink tea but not coffee? Oh, I need to finish this, don't I?
25.
Okay, so I need to finish the deal. So how many tea drinkers are there total? 36, I already have 11 placed, so that is 25, that's correct. How many coffee drinkers do I have total?
7.
18, so there are 7 left that are only coffee drinkers. Sorry, I forgot to finish my Venn diagram already, okay? All right, now we said, how many of them drink tea but not coffee? That's the 25, right? That is 25 out of 53. I've got to write it as a fraction or a decimal because it's probability, okay? If you just said it's 25 on that one, you wouldn't get full credit, okay? Now, the next two kind of are weird, all right? What is the probability if the staff member is a tea drinker, he drinks coffee as well?
So that's
Another way of saying that is, what is the probability that the staff member drinks coffee given that they're a tea drinker, all right? So what we would say is this, the probability that we drink coffee given that we drink tea. Okay? There's 2 ways we could solve this one. All right? I'm going to show you both ways. I don't care which way you do this. If we were to do this using the formula, we would go the probability of coffee and tea over the probability of tea. Anytime you're using this formula, whatever the given is, coffee given tea, the given part is the denominator over here. All right? So the given part is always the denominator. So what is the probability that I'm a tea drinker? 36 out of 53. So 36 out of 53 is the probability that I'm a tea drinker. What is the probability that I drink both? 11 out of the 53. Now some of you going, man, that's a complex fraction, I don't like that. Well, what's the good news about the complex fraction?
They have the same denominator.
They have the same denominator, both 53 at the bottom. So technically those cancel out. You could keep, change, flip, they would cancel. And so my answer would be 11 out of 36. So the probability that I drink coffee given that I drink tea. All right? Now, here's the other way to look at it. If I've got my Venn diagram drawn, I can use my Venn diagram. What's the probability I drink coffee given that I drink tea? Well, how many people drink tea? 36. I'm only going to look in this circle. Given that I'm in this circle right here, there's 36. How many of them in this circle right here drink coffee? 11. So I could do it that way as well. Okay? So that one's easier if you had the Venn diagram, right? Okay? But if you didn't have the Venn diagram and you had the formula, all right, that's another way to get around it.
Most of the time, are they gonna give us the same like denominators, so that it'll cancel out?
Yeah. If you set this up, this whole formula works that way so that those would set up.
Wait, so like on the test, is it gonna be like clear, like what's going on? Or are we gonna have to,
Yeah, it's not gonna use this. It says given.
Okay.
All right. And most of the problems that I've seen, they use the term given, and they're
like also like for like the other formulas too, like will it be? Like,
yeah. You're looking for like if it's independent, I know I'm gonna go use the independent formula. If it says mutually exclusive, then I'm gonna go look at mutually
Okay,
exclusive.
so it's gonna tell us.
If it says conditional or if it says given, then I know I'm using this formula.
All right.
Do they
Okay.
tell you what topic the questions are, or do you have to figure that out?
Like on the
Like
main one.
Yeah.
No, but I think they give you enough information in there that you can kind of know where it's coming from. Okay, let's do the last one here. What's the probability that I'm a tea drinker and I don't drink coffee? So given that I'm a tea drinker, I don't drink coffee. If you wrote that, you would say probability of not a coffee drinker given tea drinker. And so that would be those 25 out of the 36 in that circle. Okay? So I'd have that. Okay? All right, let's take a look at a couple last problems. Here's some dependent or conditional probability given some dice. They did say number cubes. Sometimes they'll throw that in there. For the rest of the world, they refer to them differently. All right? So if I have one that's red and one that is blue, explain why the events are dependent and then find the probability. Okay? So the first one says the red cube shows a 1, and the sum of the two are less than 4. So again, it's that situation. I roll, and when I roll, I have a 1 sitting right there, and I need to roll a sum less than 4, all right? Is this a dependent thing? Because I rolled that one, does it affect what I can roll in this one? Yes, it does. So this is a dependent situation. All right. Now, if I were to write this, I would say the probability that I have a sum less than 4 given that I have a red 1. Okay? Which would be the probability of a sum less than 4 and a red 1 over the probability of a red 1. So I could write it like that. Now, I'm going to show you both of these. You could think through this one kind of logically, or we could use our formula. We can use our sample space diagram from yesterday to help us with this as well. Okay. So if that's already in place, if that 1 is there, then how many results could I have when I roll this one? How many results could I do when I roll a die? 6 results, right? I'm no longer 36 because I've already rolled one, right? It's already stuck. So I have 6 results here. How many of these 6 results would give me what I want? The sum less than 4. 2. If I roll a 1, if I roll a 2, I would have a number less than 4. Okay? And so there was 6 in my sample space. There are 2 that work. So you could say 2/6, or you could say 1/3. Okay. Now, I'm going to work the formula for this one as well. All right. So if I were to do this, I'm going to go back to this picture from yesterday. All right. So we drew the sample space diagram yesterday. All right. The probability of the given goes on bottom. What is the probability that I roll a red 1? Well, if I say these are my reds and these are my blues right here, how many things are in my sample space? 36. How many of them contain a red 1? 6, because we're talking about this column right there, correct? So you see we've shrunk the sample space just to these 6 right here. But if I was using my formula, I would say this right here is 6 out of 36. Okay? Now, what is the probability that I have a sum less than 4, and a red 1? Okay? So sum less than 4 and a red 1. I'm not going to go in and fill in this whole table from yesterday. All right? But this was 2, this is 3, this is 4. The sum less than 4 would only be these 3 things there, but I need a red 1. It would be these 2 out of all 36 of them. Okay? So if I were to go back over here, this is applying my formula. So 2 out of 36. And now we got that same kind of situation that we had a while ago. The 36s would cancel. I have 2 out of 6. And I have. Okay? All right. Let's do one last one here. All right, we're going to end on this one. The blue cube shows a multiple of 3, and the sum is 8. So the blue cube shows a multiple of 3. What is a multiple of 3? 3 and 6. So I'm counting by 3s is what I'm doing. All right? When it says multiple of 3, count by 3s. 3, 6, 9, 12. Those are all multiples. All right? So the blue is a 3, or the blue could be a 6. Okay? So that's what the blue is. Now, if I roll a blue 3, how many options do I have on the red one? How many total options do I have?
6.
I have 6 total options on that one, correct? If I roll a blue 6, how many total options for the red one do I have? 6 again. So how many are in my sample space? 12. So if I went back to that sample space that I did a while ago, I would circle 2 rows. I would circle the row with the blue 3, and I'd circle the row with the blue 6. There's 12 spaces there. Now, how many of these 6 right here work for the blue 3? Just 1. I need a red 5. If I get a red 5, then I get my 8. So there's only 1 that works there. How many of them work here? Only 1. I gotta get a 2. If I were to roll a 6 on the blue, I gotta roll a 2 on the red to get the 8. So there's only 1 that works here, there's only 1 that works there. So there are 2 that work out of all 12, which would mean I would have a 1/6 chance of being able to do this. Okay? That was just a little bit weird, all right? But again, you could draw your sample space diagram, you can draw your Venn diagram, you could use your formula, or whatever else we're doing this. Okay? All right. We have about 4 minutes remaining, all right? I'm gonna go over page 373 tomorrow, all right? And 376 and 379, okay? So we're not gonna do 385, we hadn't got there yet. So 376, 379, but what I'd like you to do on 376 and 379 is I'd like for you to do the odds. Okay? So on page 376, do the odds, page 379, do the odds. Okay? So that kind of condenses it a little bit for you.
326